Hi friends, welcome to Follow Up. Let's have a look at another hard problem, problem 940, distinct subsequences 2. In this video, we are going to explain a solution based on dynamic programming. So this problem statement is very short. Let's read it through first, and then we do a walkthrough, and finally we share the code and explain the logic in between. So here we are given a string s. We want to return the number of distinct non-empty subsequences of s. So since the answer may be very large, so we want to return the result modulo a constant. So here we have 3 examples. In the first one, it returns 7. So it lists the 7 distinct subsequences in the explanation. In the second and third example, the returns are 6 and 3 respectively. Notice that in example 2, a appears twice, and in example 3, so the a appears 3 times, and in this example, there is only one unique character, that is a, right? The constraints are the following. The length of s is bounded above by 2000. And s consists of lowercase English letters only. So this s consists of lowercase English letters will be important for our solution. So here our strategy will be dynamic programming. So basically we want to do a linear scan of the string and count in the process the different subsequences ending at different characters. So here, let me give you a walkthrough for example 1. So here we have a string that is ABA, right? Then we want to initialize a sequence, a list, array, or dictionary. So here, let me use dictionary. So here, these are the characters. Let's see, lowercase English characters. There are in total 26, right? So here, there's a character and there's a count. So this is the number of valid subsequence ending at this character. For example, at the very beginning, there is 0 subsequence ending at a. There is 0 subsequence ending at this character b, right? So on. And then we are going to do a linear scan for the string at index 0. So the character is a, right? So then in this case, so we can add or append a to each of the sequence in the previous state. For example, I can append a to all the counts of sequences. So in this case, our update rule will be the sum of the end and count values, then plus 1, because this character itself can serve as a non-empty subsequence. So in this case, that's we update because the sum of these values is 0. So then we have a1, all the other characters corresponding to count 0. So this means that there is one non-empty subsequence ending at this character a. Then at index 1, so we have character b, right? So then the sum of end and count will be 1, right? Then 1 plus 1 will be 2. Then we are going to have, so this is the previous state for a equals 1. Then b is 2. What does this mean by 2? Because originally at each of the ends we can append b, right? For example, we have an a, so this corresponds to 1, right? That is a. Then we can append b, so we are going to get ab, right? Then b itself is a valid subsequence. We're going to have b. So this b has a value 2, means we have 2 non-empty subsequence ending at this character, right? This is the dictionary state a1, b2, and others corresponding to 0. Then look at index 2, we have another a, right? Then in this case, the sum of these dictionary values is 3. So 3 plus 1 will be 4. Then we update the value of a to be 4. So this we have a equals 4, and b for 2. So what does this 4 means? So originally we have a corresponding to 1, b corresponding to 2. This corresponds to 3 subsequences, right? And then if we add b, right, so we're going to have produce 4, right? So for example, you have, this means you have AA, right? Then we have ABA, right? So we have and BA. So this is corresponding to ending at A. There's 1, right? Then we add this A. There's ending at B, we have AB and B. We can append A in both the two instances. Then this A itself is also a valid subsequence, so we have 4. Then in this case, ending at this letter A, we have 4 distinct. Ending at letter A, we have 4 possibilities, right? Then at B, we have 2. So together, we are going to have the sum of this is 4 plus 2, that is 6. So this will this finishes the walkthrough for this dynamic programming procedure, especially the DP update rule. So now let's look at the coding. The coding actually is very simple. So here we use dictionary. So in order to compute the sum community, we are going to use array. So here we can use the ordinal number of this lowercase English letters to as the key for the end and count. So here let's end and count. So I'm going to use 0 times 26 because there are 26 lowercase English letters. And then we are going to another thing I want to mention is that we need to return modulus constant, right? And then what we want to do is for end character in S, right? Then we are going to do the update. So let's first find its index. So this corresponds to end minus the ordinality of A. In other words, we are using relative indices. For example, A corresponding to 0 and B corresponding to 1 and Z corresponding to the last index, that is 25. Then the update will be end at count at this current index, and then it equals a sum of the previous state. So that's why here we use this list, because we can directly use the sum function. If we use dictionaries, we need to sum end and count values, right? Then we need to add 1. Add 1 means that the current character itself can be used as a end or used as a single character valid subsequence. So afterwards, so let's do this set by modulus constant. And then we are ready to do the return. So we return mod modulo, not mod. So the sum of end and count modulo this mod. So this sum means afterwards we get the summation. So because there's only 26 characters, so we find the corresponding number of subsequence ending at those characters, and then we sum and modulus constant. So with that said, basically we finished the coding part. So I would suggest that you digest this walkthrough again and make a connection with other data structures and or even other problems for this one. So the coding part, if we directly write this, actually is very simple. So you can see, right, the time complexity will be O of n, right? So if we see the computation of the sum, let's use also 1 unit. And the space-time complexity will be O of 1. In case here we have 26 characters, right? But we have a big constant, right? So with that said, I guess basically that's about it for a specific solution. Now let's do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So I would say that's basically about it for this specific video. Thank you.